we can try it. But I think, right now it seems to be okay. Feel free to just shout in the middle if, I know sometimes like.
That is not a good sign.
And if that becomes a problem.
Sorry, the stream started, so you are free to start streaming.
Okay, excellent. Hi, everyone. This is the keynote for both the ISSTA Summer School and the ISSTA Doctoral Symposium. And our keynote speaker in this session is Dr. Professor Claire Goues from Carnegie Mellon University. Her research spans a wide range of software engineering. I'm not going to list all the specifics. What I will say is that she's the 2020 recipient of the SIGSOFT Early Career Researcher Award, which means that when I first heard one of her talks in 2012, she must have just finished high school. And look how far she's come now. So Claire will be speaking to us about automatic program repair for early career researchers. And I'm going to hand over to her now.
Thank you, Jacob. I think while you were speaking, I think I did not diagnose, but I may have rectified some of the things causing my internet stability issues. So I only caught half of your introduction, but the half I heard was really kind. Thank you. I will start by sharing my screen and then do some preliminaries. So I'm very proud of myself because it has only taken however many months of working remotely for me to reliably remember the order of operations for how to start a presentation in Zoom and then share it. Here we go. I am optimistic that you can all see a slide that is blue, that has some logos on it. So unless anybody protests, I will continue as though that is true. I just want to make sure I have the chat window open in case there are connectivity issues. And then if anybody complains on the chat during my talk, I will be able to see it, hopefully. Start moving things around my windows to get a good setup going. Okay, so this is kind of a funny talk because it's serving two different masters. As mentioned, this is a keynote for the Doctoral Symposium, and those talks are often a bit kind of personal in terms of personal trajectory, discussing some lessons about science that somebody has drawn from their career so far. And it's also a talk for the summer school participants about the subject of automatic program repair, which is something I've done a fair bit of research on. And it's a nice sort of confluence of subjects because I did my dissertation on automatic program repair. I graduated in 2013. So I'm trying to give a talk that kind of overviews the lay of the land and some of the challenges and the progressions of program repair, sort of through the lens of this work that I did early in my career and that has progressed sort of to today. So hopefully that works. It does mean I had to make some choices in what I focused on in terms of program repair. I don't think I could have done justice to all of the great work that's happening in the field in an hour. But I did, in the end, I'm focusing a lot on some of the early work, some of my early work and some of the other early work. And I think paying a bit of short shrift to the stuff that's happening more recently, just because of the nature of the talk, which I feel bad about because there's some great work that would be fun to talk about instead from all sorts of different groups in the world. So hopefully if you find it interesting, you will be motivated to see what's going on in the field over the last couple of years, since I won't be able to do as much justice to that as I'd like to. So that said, I've also set this up to have breaks at regular intervals to do questions. I feel like we made a lot of progress and innovation on how to do, more interactive sessions, certainly in a class session remotely. I haven't quite figured out the best way to do this for a keynote setting, like where we are now. And so instead of trying to do any kind of fancy interaction thing or activities, because I don't think it's appropriate for the nature of the talk, instead I put slides in throughout, excuse me, to remind myself to pause. So I encourage you to put questions, I think into the Slack channel is what we were discussing before the talk began. I think you could probably, if you can't find the right Slack channel, the group chat in Zoom would work as well. You're also welcome to raise your hand at the point of when I pause to ask questions, and I'd love to hear them. The goal is to kind of break this up so I'm not just droning at you for 45 minutes and we have a chance to have a bit more of a conversation. So with those preliminaries, the name of the talk is Do What I Mean, Not What I Say, an introduction to automatic program repair for early career researchers. And I'm Claire Goues. I'm an associate professor of computer science at Carnegie Mellon. Carnegie Mellon's a funny place. It's got a very large faculty and a school of computing instead of just a single department. And so we have 7 departments in a school of computing. The naming and organization of those departments can be a little bit opaque or difficult to explain to outsiders and to insiders. So instead of doing that, I'll just tell you the name of my department is the Institute for Software Research. And among other people, it hosts the faculty who do traditional software engineering research, people who publish in places like ISSTA and ISSTA, as well as probably about half sort of the people you think of as doing traditional programming languages research. But that said, my title is, I'm a professor of computer science because we're all professors of computer science. I need to make sure I have the right thing so I can advance slides. Did my master's and PhD degrees at the University of Virginia. I put the dates up here to emphasize sort of a useful lesson for those grad students in the audience who are earlier in their doctoral programs. I wrote out the last financial crisis in grad school, and it was the choice of champions. So I encourage you to do the same. I have tried throughout this talk to insert questions, to seed questions in your head. So if you see some pop up, you don't have to ask those questions, but I really want you to think about questions if you want to ask them so that we can have a conversation. So that said, talk time. So my whole career so far, both in industry and in research, has been basically defined by bugs. And I have something of a sort of a powerful story about how I was chased back to grad school from my software engineer position by a particular nasty customer bug report. And I'll spare you, but I think it's informative as a story because I joke, but really a lot of my research so far has been sort of dictated by this problem. One of the sort of running themes of this talk that I want to emphasize to you is that program repair is an interesting subject. I think it's cool for a bunch of reasons. And this is sort of reason number 1. Program repair is cool because it's about bugs. Bugs are a really fundamental problem. I mean, it is the problem in software engineering, right? I mean, we want to be able to build software in a way that's correct, that doesn't have mistakes in it, that does what we want it to do. And so this very central issue in the problem of building software and in programming is the core issue in program repair. And, I use the word bugs sort of very colloquially. I mean, I think in general, software quality is a very interesting problem. Although my dissertation work and a lot of the work of my group still is focusing on program repair. I've been a professor for longer than I was in grad school. And so now, of course, my group does other things besides program repair, but it's all under this big umbrella of software quality. But the program repair problem in particular is a sort of a particular issue that we're focusing on today. So I'll set the stage for you in terms of what the problem statement is of this area of research that I'll be overviewing. The key issue is that we're going to have as input a program. And this program will be doing many things correctly because most programs do most things correctly eventually. But it will be doing at least one thing incorrectly. There's a mistake that we would like to be rectified. In practice, there's many ways, of course, that you can identify a bug or describe a bug. You can use analyses of various kinds, steps to reproduce customer bug reports. But in the kinds of program repair I'll be focusing on today, we're using test cases to identify behavior that we either want to preserve or that we want to change. So when I say that there's a bug in a program in this setting, I mean there's a test case that's failing and we would like it to no longer fail. The goal of program repair is to develop some magic. The unicorn is what comes up when you search the Apple icon library for the word magic, to produce a small set of changes, a patch, the same thing a software engineer would try and build. Then when you apply it to the input program, produces an extremely similar program. It passes all the same previous test cases, but without that one failing behavior that we were trying to rectify. Now, I want to emphasize that this is a different goal than you may have encountered in other analysis or security research. So the goal here is not to preclude entire classes of errors or vulnerabilities. We're not producing analyses that can eliminate all buffer overflows or information leaks, for example. Instead, it's this more general developer-facing use case, right? I have a bug in a program. I don't know what it is, except I have some evidence that it exists, and I would like to fix it. Now, there has been, as I'm sort of implied, quite a bit of research on this over the last 10 years, but the high-level paradigm of this problem is roughly the same kind of issue that we're trying to solve in all of these problems. This is fundamentally a search problem. There's a very large space of possible changes we can make to a program to fix a bug, and we want to narrow it down in a way to make that problem tractable. So step one is the same thing that you would do as a programmer to try and fix a bug. You'll try and localize it. You might stare at it a little bit to analyze it and try and understand what's going on. You'll then have a set of strategies to create or combine fix possibilities into one or more possible patches that might fix the bug, each of which will then be validated. So we might make 50 of them and try them each in turn to see if they fix the problem. Now, as I said, because of the problem setting, the way we're validating candidate patches and the kind of work I'm overviewing today is by using tests. We're going to apply the patch to the program, run the tests, and see how many it passes. So that's going to be basically the same for any of the kind of work I'm talking about. Especially recently, there's been interest in moving into using other kinds of quality signals. Other static analysis especially is gaining a lot of interest in sort of the program repair setting. So I don't want to pretend that test is the only way this works, but just imagine that it simplifies the explanation. So this is where I think a lot of the core innovation is happening in terms of when you begin to get down into the weeds about how these techniques work. And another thing I really like about program repair is really called out. It's cool because it can basically pull in all of testing and analysis. Localizing the bug, that especially at first, there's a little bit changed in the last couple of years, but really a lot of that kind of bug localization is really drawing on existing work in fault localization, in spectrum-based fault localization, and adapting existing analyses to this new setting. And there are a number of other analyses like looking at which variables are implicated, in which possible predicates are being violated on a particular buggy run of the program. There's different kinds of analyses that we can pull in and throw at this problem to learn about what possible good candidate patches are. So one reason I like being a professor is that I really like learning about new things, right? I get to do that all the time. And program repair is a really great area to work in for that because there's always room to learn about some new innovation in program analysis and testing and try to apply it. It does mean in practice, one becomes sort of a dabbler in all analyses and perhaps a master of none. But it is nice for somebody who likes to learn about new analyses all the time, which I do. So if you imagine that fault localization is really also very commonly the same between all different techniques, we can begin to focus on this part, which is where I think a lot of the real distinctions lie between different techniques. And one common breakdown in terms of categories of program repair techniques is between what we call heuristic techniques and semantic techniques. I'm overgeneralizing, but I think it will help give you the spirit. So let me illustrate a little bit the differences between these two classes of techniques. Heuristic-based techniques, the idea here is that we'll have a set of edit templates that we have defined, things like delete a statement or wrap a statement in a null check. We'll have maybe a set of these strategies or edit kind of templates that will apply. And then we're going to use them to manipulate abstract syntax level, tree level constructs. But these constructs will typically be fairly coarse. So heuristic techniques, I don't think I know of any that will try and, change constant values within a program or manipulate very low level expressions, right? Because that's a very large search space. And so to keep it tractable, they tend to be kind of these higher order templates, things like wrap something in some kind of check or, delete or move code around at kind of the line level. And then the trick is kind of what are the templates being applied and how do we choose between them? Some strategies are deterministic or just sort of informed by decision trees. Others will use stochastic or metaheuristic search to traverse the space. Semantics-based techniques are sort of very different. They are more likely to manipulate lower level constructs, not lower level, but sort of finer grained constructs in the abstract syntax tree, particularly expressions. So things like the right-hand side of assignments and sometimes conditionals. And they do that because these techniques are predicated on the use of synthesis to try and replace those expressions with code that's more likely to be correct. So they use symbolic reasoning and the test cases to infer constraints that would inform the correct code. And then use those constraints to inform synthesis. Now, there's a whole rabbit hole on synthesis here about how we can adapt existing synthesis techniques to this problem, how we can make them more repair-oriented, how we can combine the two types of program repair to make each of them better by taking insights from the other. But the real core difference here is kind of this heuristic templated approach versus something that's predicated on the use of synthesis and constraint solving. I'm about to show you 2 bugs and 2 fixes, 1 fix for each bug. And they're different bugs. I don't want to walk through them. I just want to show you what I mean in terms of kind of the kinds of patches that each of these techniques are going to synthesize. So on the left, here's a small piece of code. There's an infinite loop in this program that can be fixed if you delete this arithmetic on line 6 and then move it between lines 8 and 9. You'll notice that this is a sort of high level, line level code movement kind of edit. So we've deleted something and we've inserted it elsewhere. On the right, this is a snippet of the code from the Hartley vulnerability with a patch that has been synthesized by a semantics-based technique. And you'll notice that that patch is manipulating specifically this condition on line 1. It's added constraints to that condition. So you'll notice that these are very, very different types of code that are being manipulated here. There are often the case where these kinds of techniques can fix the same kinds of bugs, but the patches they produce tend to look very different. There are many ways to fix each bug. There is overlap in what these kinds of techniques can do, but they don't tend to produce the same patches. Now, like I said, many techniques combine elements of both. Forgive my overgeneralization, but that kind of gives you the high levels. So here's where I pause and see if there are questions in the mysterious Slack that I cannot see.
Okay, let's check. No questions in Slack. And Claire, I'm not exactly sure where your talk is going, but I thought of at least one question, and that is this used in industry?
I love that you're asking me that question because it is like the literal next slide I'm getting to. So
okay,
why
excellent.
don't I do that?
Good.
Did not plant that. I am hoping to sort of pause and just, I wish if we were live, I would do what I do in class, which is pause and stare at the audience until they ask me questions. But I'm so excited by this transition that I'm just going to do it. So a second reason program repair is cool is because it's an industrially relevant problem. I'm so excited by this question, Jacob. And it's clear it's an industrial relevant problem because bug fixing, bug tracking, bug triage is something we know it takes up a lot of developer time. And so one of my sort of favorite recent examples of a paper that describes some program repair in practice appeared in 2019 in the ISSTA SEIP track, comes out of Facebook. They describe a system called SafeFix, which is automated end-to-end repair at scale. It's actually more sophisticated than what I've been talking about. It both finds the bugs using automatically generated tests and then fixes them. It is extremely cool. And they describe in the first paragraph that it's sort of predicated on this paradigm that is typified by something they call GenProg, which we'll get to in a second. And they describe results from repair as applied to 6 multi-million line systems, which is really cool. There is some other evidence. I'm kind of seeding my own question, but unless this is a useful transition for me to get into some of the earlier work. So this is now arising kind of more in practice, especially as continuous integration pipelines are becoming more common. And there is evidence from a number of places, not just Facebook, although Facebook is gracious enough to publish about it, that this kind of work is gaining more acceptance as part of your standard development pipeline, which I think is really cool. But I'm going to, having done that segue, talk about GenProg because, like I said, it's a doctoral symposium talk secretly. And so we want to talk a little bit about my work. So GenProg's a technique. This paper was either my first or second paper from grad school. You see my name is third in the list. It appeared at ISSTA in 2009. We extended it for a journal paper that appeared in 2012. Those are the dates on that journal extension. Actually the subject of my dissertation ultimately was automatic program repair using genetic programming. So it's worth, I think, talking a little bit about what GenProg is and some of the lessons that came from its development over 10 years that got us to Facebook. So the idea behind GenProg is to automatically repair bugs and off-the-shelf unannotated programs, the same kind of problem setting I've given you. And the idea is to use a biased random search through the space of all programs for a version that fixes the problem. The search we use is genetic programming. It's the application of evolutionary or genetic algorithms to program source code. And so you can see how this fits in the heuristic model that I told you about. We have 3 very high-level kinds of edits that we're going to be searching over. We're going to replace statements and delete them or insert one after the other, and that's it. And we're going to use a genetic programming heuristic to choose edits to combine and to modify and to sort of define the search problem. So this is the slide from the original talk that gave the experimental results. It was 2009. And so when I asked my advisor, how much code do we need for this results section to be reasonable? He said 50,000 lines. I overachieved. I was extremely proud of myself. And now it's funny because the smallest program in your sort of typical program repair evaluation paper is going to be more than 60,000 lines of code. But you might say, okay, like, how did we get from here to there? Because the Facebook paper, says, hey, GenProg typifies this thing. How did we get from this, 60,000 lines of code to 6 multi-million line systems? And that's where I think some of the lessons that are interesting to talk about the development of this area come from. One possibility is that we were just right. I was just a really precocious second-year grad student. And I happen to, we worked on this project and my advisor's really smart and our colleagues are really smart and we just had to wait for Facebook to take an interest. I will tell you that is not what happened. Because basically every design decision we made in the original algorithm was wrong. And I'm not exaggerating when I say that. So one problem in a search, kind of a key issue in search strategies, is how do you represent the candidate solution? We represented candidates as entire programs that were being evolved towards a solution. This is a very evocative analogy, but it doesn't scale at all. It didn't work at all when we applied it to large systems. We had a bunch of heuristic weighting schemes that we used for how to prioritize test cases, how to do the fault localization. We used our intuition and it was just all wrong. We had this insight that if we used delta debugging on the produced patches in the end, we'd end up with higher quality patches. And if we paid any attention to the machine learning literature, we'd have known that that was unlikely to be true for various reasons. And we had, we were implementing a genetic programming heuristic where there are all these sort of specific kind of algorithmic concerns like selection and crossover. And all of the implementation choices we made were wrong. I highly encourage you to read below the fold on Wikipedia when you choose to implement core algorithms outside your wheelhouse, because right as you scroll down, it'll describe like the first way to do a thing, and then it'll say, that way's bad, use this way instead. We never got that far. So I'm telling you this because it's, I think, an important lesson for early career researchers, which is to not let the perfect be the enemy of the good. I think that this actually applies to not just, particular research projects, but I find myself saying it to my own students a lot that, let good enough is what you need to make scientific progress, and don't let perfection stand in the way, because if you have a good idea, you can explore it without getting every element right the first time. I sip my coffee and I wait for someone to check Slack. I will say, to expand to Jaco's question, actually, that Facebook's not the first company to have published about its use of this kind of search-based program repair. There's a company in Iceland, sort of healthcare IT company, that published about it first. I want to say as early as 2012. And so, not all companies are using that talk about this are using search-based strategies, but there is some evidence that there is a sort of acceptance of this idea of sort of a search-based approach to program repair, which I admit surprised me.
I'll also admit there's nothing on Slack for now,
okay. But
I'll also admit that my actually there is a question. Shuvik asked that while validating multiple patches, is there some kind of prioritization scheme when you have multiple patches to evaluate?
So this is a good question. This does vary by technique. Some techniques will simply generate a patch and then validate it and just go in order like that. And so there, the heuristics will be more oriented towards which patches do you generate first. So in the semantics-based techniques, for example, you can modify the synthesis heuristics to prefer, for example, small changes to the program. So the goal here would be to generate patches in increasing size difference from the original program, with the idea being maybe that's more likely to be a readable or a preferable patch. This is a this is an open problem, right? If we have two patches that both lead to the same test case behavior, how do we choose which ones to prefer? This is something that basically, this idea of repair quality is kind of the core outstanding continuing issue in program repair, something I will talk about as we progress. And so there are a number of strategies there, like similarity to the original code, like similarity to previous code or previous changes in the code base that we can use to make decisions to choose between patches. It's a great question.
And Claire, I'm very sure I'm not going to predict your next slide again, but I wanted to ask about industrial acceptance. Do you think people or companies are more prone to adopt localization as opposed to repair because they don't trust the repair methods?
So this is an interesting question. I think, okay, so I think that my prediction here is that in industrial settings of repair is actually sort of almost using it as localization in some respects, because the examples I know of where this is being accepted, it's integrating program repair into the existing continuous integration pipeline, where you have a developer who will check the patch before it's automatically deployed. And so if the patch is wrong, then they can make changes. But there's also evidence that having patches, even incorrect patches, can help people debug more quickly. So if you know, and I can totally see this, I spent a lot of my career staring at patches that are weird, and it helps me understand the bugs, because it's like, oh, well, that's not right because, oh, but I understand. So I think localization or analyses like that help debug are more likely to be accepted than just automatic patching with no human in the loop. And I think I don't want to make strong predictions. I think we may be a while from the no human in the loop kind of repair, at least the general cases. I think that there are some contexts where it's appropriate. Like if you have some intrusion detection system running on your server overnight, automatic detection of an intrusion and mitigation strategies, that's kind of program repair, right? So in these sort of constrained environments, if you allow program repair to do very constrained things, I can see some adoption there. But right now, I think the human in the loop kind of checking of patches before they're deployed, that's kind of the MO that that industrial uptake seems to prefer, which makes tons of sense to me. So I'll keep going. So actually how we got, or how program repair got from 60,000 lines of code to 6 million, there were conversations with practitioners very early, because they would listen to talks about program repair and say, hey, that's really interesting. They see a slide like this one. They'd be like, that's cute, but if I gave you the last 100 bugs from my actual project, how many could you actually fix? Which is a very different question. And to answer it, kind of the last work I did in my dissertation was to build a fairly large data set of real world bugs in real programs. And I did this in a way that will probably sound fairly typical now. I work backwards in time through source control. And you can see how old I am by looking at the open source repositories I was using, looking for places where bugs were fixed. And this led to a data set we called ManyBugs that have since been, that I used to evaluate the technique at the time, but I had to drive a number of algorithmic changes, because if you remember all those incorrect design decisions, they all manifested very quickly when we started to run on really large programs. We actually ran these experiments it's possible this is the talk that Jacob remembers from 2012 on Amazon EC2, which despite being actually out of beta in 2009 was quite young and fresh still for the purposes of software engineering research in 2011. And we were fairly early adopters and ran into all kinds of funny corner cases. But here is, I think, the important point, which is that by running on real indicative open source programs, by trying to answer this question that engineers actually had for us, we were able to find all of those places in those design decisions that were incorrect, which is something, you know, I think allowing sort of the useful or the actual practical use case to drive our evaluations really helped us revisit a lot of our assumptions. We released that data set, and it really drove scalability. So both heuristic and synthesis-based program repair techniques had to undergo fundamental reconfigurations to enable scalability. We moved from involving entire programs to involving just patches. Simultaneously, semantics-based repair also, there were some really cool innovations in representation to go from having to reason about the semantics of an entire function to just the semantics of the change that was required to make the program better. And so what's cool here is that we have this shared data set of real world bugs and the ability to compare on it because we all released our code, and that really drove innovation in test-driven program repair and allowed us to make these fundamental reconfigurations to enable scalability. So my lesson here is release your code. I'm sure I'm not the first professor to complain about this. I'm not perfect about this. My students aren't perfect about this. I do yell about it a lot. And I understand why it's hard because releasing code takes time and energy that typically does not lead to another paper. I have a benchmarks paper that I have a citation for in the previous slide. It's a huge amount of work. Most of the time it doesn't lead to papers. You don't want people digging through your code, but it supports extension and comparison. And it's really a cornerstone of the scientific process. And it's really a cornerstone of impact because when people are comparing to you, that drives going. And the second lesson here is that the impact of the GenProg project and of the subsequent work in program repair really arose from more than one paper. Revisiting all of those design decisions, that wasn't just one paper. And those papers are harder to publish. To being perfectly honest with you, it's a lot easier to publish a new flashy paper on, with a new algorithm for program repair than it is to revisit all of those design decisions. But ultimately, it's the body of work that matters. And so even if it is kind of less shiny in terms of actually watching the work progress, it's kind of some of the more important work. So Jacob didn't anticipate my last transition, which is fine.
Not exactly.
But I want to take a second here.
Let's see, we don't have any new questions at the moment.
Okay. Well, then I won't let you try and guess. I'll just keep going because this may be the thing that, this is the thing that kind of came up in the previous question, which I think is a good one, this next segment. So I spent a lot of time in the first kind of part of this talk and a lot of the work in program repair focused in the first 5 years or so on scalability, and evaluating on these big shared data sets helped us get there. We're also trying to look a bit at expressive power, how many different bugs could we fix? These are two kind of core challenges in getting to industrial relevance. But of course, the really big one is repair quality. I said we're using tests. And this was a really controversial decision, actually. It has led and it continues to lead to a lot of debate in program repair and sort of adjacent areas about whether tests are suitable, whether test suite quality is sufficient to actually assure that the patches that you're getting are good enough. And this has been a problem. It's sort of a known issue that we have been talking about since day one, because actually our very first set of experiments kind of illustrated how important this was. I'll tell you about those first experiments, the ones I was proud of. We actually had a bug in a very simple web server called KnowledgeGPT. It has very basic get and post functionality. And the first version has a remote exploitable heap-based buffer overflow in the handling of post requests. So this is a nice setup for program repair because you can make a test case to see if you have this bug by running the exploit just to crash it. You actually could get access. You could actually literally get root on a machine by taking advantage of this, but we don't have to do that to test whether the vulnerability is still there. We just wrote a test case to run the exploit to crash the server and then see if it was still running. And then we needed a bunch of passing test cases to make sure the web server did useful things. And so sat down and wrote some easy passing test cases like get indexed at HTML or get not found at HTML. Because we're just like sitting at a desk like, top of my head, like how do I test a web server? And so if I were in a room with you all, I would say, what do you think happened here? But I'm not. So I'll just tell you what happened here, which is that our program repair prototype found a patch very quickly. To pause and see if you can guess in your own minds, that just deleted the handling of post requests altogether. Now, I, at this point, am typically willing to fall on my sword and say that I prefer that. So a web server that can post static content to a web server that is exploitable in the way that KnowledgeDPD was exploitable. Like, I think this is better than nothing at all, but I don't think it's better than an actual fix. And once we added a benign test case that tested post functionality, the prototype could find a good patch for it. In fact, it reuses a content length check from elsewhere in the program. It's pretty cool. But it shows you how important test suite quality is, because if you leave off that test, you're losing some functionality that you don't need to lose. That said, though, how much test suite quality matters is kind of a different question. So in that endless journal extension, we did a set of experiments that evaluated this scenario that I kind of alluded to in an answer to Jaco earlier about, imagine you have a long-running web server and an intrusion detection system that could find when you're being attacked and then generate repairs for the detected anomalies. We had these indicative workloads that were just a bunch of unfiltered requests to the UVA computer science web server and a PHP room reservation application. So this is like actual requests that people made to this PHP application. So, the indicative users being the UVA, computer science department. We had a couple of web servers with vulnerabilities in them. And a web server, I think this was just like with PHP enabled, with a patch to a bug or a vulnerability in the PHP interpreter that was bad. So the point is that we configured the program repair system to try and fix this bug, and it just couldn't find a patch that didn't just delete code that was under tested. But our goal here was to see, well, what was this actually the effect of this patch, right, on the actual indicative user experience? And the answer is that it had basically no impact on the indicative user experience. Even when we deployed the patch that deleted code, the web server could handle all of the same requests as it did before with the same, expected user experience, right? User would not have noticed if this patch were deployed in production, which I think is really interesting, actually. It speaks a little bit to kind of the nature of bugs, which is that they're typically on corner cases, right? This particular bug was in a very obscure corner case in the substring replace function in the PHP interpreter that, the average PHP programmer wasn't really using. And so turning it off wasn't bad. The user wouldn't have noticed at all. This is something about the nature of programs. So this gets back to my first lesson, which is that we shouldn't let the perfect be the enemy of the good. And it also speaks to the fact that test cases, although they are imperfect, are actually not a terrible way to help guide program repair, even if they need to have additional support to give us sufficient assurance in patch quality for use in practice. And in fact, it's still a very common setting for program repair research today is to start from the test cases and then use other heuristics, other strategies, or other quality signals to help assure patch quality once it's produced. Like I said, there has been work moving both industrial research and academic research towards trying to repair statically identified bugs in programs, and I've done some work with this myself, but it's very standard practice to use test cases to evaluate patch correctness. And this is good because tests are useful and they integrate very naturally into existing QA practice because of this rise of continuous integration pipelines, right? There is a lot of standardization of regression testing pipelines that is really kind of supporting the adoption of this kind of technology in practice. But I will say that continuous integration has arisen since 2009. As a common practice, it really arose with the widespread adoption of cloud computing. So in 2009, the use case was actually complete nonsense. Now it makes a ton of sense. Be like, oh yeah, your CI, it detects a failure. Let's launch a program repair approach, you know, like, but in 2009, this didn't make any sense at all. And people didn't call us on that as much as I think they should have. There was a lot of controversy about, well, our test case is good enough. Are they going to give us patches that are good enough? But not enough, I think, focusing on this use case. Although I guess in practice, it doesn't matter, since in practice, the practice caught up with the research. But if it hadn't, I probably wouldn't be having this conversation with you. So my lesson here is that, you know, it's okay to do research that's ahead of practice. You know, it's better, I think, if it's plausible. But one thing I like about being a researcher is that I can have a slightly longer time horizon on the things that I work on. And so can you then, if I were in an industrial, you know, strictly engineering setting where the next quarterly goals are the most important thing. There will be times that we take risks that don't pan out, where we're ahead of practice and practice doesn't go that way. But I think that that's kind of the price we pay for getting to be a bit more speculative and do things that I think are a bit more interesting in the long term.
Okay, Slack is still empty, but I wanted to ask a question about the test quality that you're referring to. And that is the relationship between coverage and patch validation. So if a patch or the code that's affected by a patch has low coverage, I mean, do you bring that into your work?
So in general, test suite quality, as measured by a number of metrics, including coverage, has a sort of positive association in general, measured in various ways with patch generation quality. It matters a bit more, you know, overall coverage matters a lot less than coverage of the actual implicated code, I think, for reasons that are probably obvious. I don't know of work that has tried to use that to predict quality, although that's kind of an interesting idea. But I do know that, you know, sort of better the test suite, sort of the better the patches. That said, we've done experiments with full coverage, you know, full branch coverage test suites of very small programs where we could have full coverage of either the input space or of the branches in a, you know, sort of known good solution. And 100% coverage does not by any means guarantee 100% quality of the produced patches. I actually almost wish I had slides on this because it's actually really kind of cool to look at this. If you take one full coverage test suite that identifies a bug in a short program and repair it, you can then take that patch and that patch program and run it on a set of another high coverage different test suite, right? Basically to evaluate the degree to which it generalizes. You think about this as sort of the machine learning analogy, right? You want to see how much you're overfitting to the test cases provided. And even if both test suites are very high coverage, overfitting happens. And it happens for, I don't know of a test case guided program repair technique that does not overfit to at least some degree. This is basically the key kind of repair quality question. So yes, coverage helps, but I don't think that it is my prediction that just making better test suites is not going to fully solve this problem. I think we need to better understand what repair quality is and use that to inform better heuristics, better patch construction methodologies to improve the probability that patches will be good. But one more thing I will say about this is that even though automatic repair techniques overfit, humans do too. So, you know, I think we tend to focus a little bit too much on the fact that, you know, we're inevitably going to overfit, instead of by thinking about what our baseline is, right? We've done experiments where we've compared to introductory programming students and kind of given them the same task, which is to say a set of test cases and try and make their programs, you know, pass them when they're held out. And introductory programming students also overfit. And on average, about the same amount as sort of existing program repair techniques. The distributions look different, but it's a thing that humans do too. So this is all to say that repair quality is a really kind of fundamental issue. Another reason I think program repair is cool because it kind of helps us try and understand it.
Okay.
That was a long answer to a short question. I'm sorry, but I think repair quality is like fascinating, and so I riff on
I'll tell
it.
you what, I mean, I just had the thought that maybe in some strange kind of way, coverage would have shown that weak test suite you had for the web server was broken in some sense, but I can't exactly enunciate how.
Yeah, I mean, I think that I can imagine a world in which you'd say, you know, basically there's no overlap between the failing test case and the passing test cases. Are you sure that you have enough passing test cases? And in some sense, this devolves to mutation testing, right? Because sort of the classic formulation of mutation testing is that you make changes and see if your test cases notice. And if they don't, then you add more test cases. So there is this duality between mutation testing and especially heuristic-based program repair that can help, I think, identify weaknesses in test cases.
Claire, we have about 5 minutes to go. Can you finish up in that time?
I can.
Excellent.
Yes, I can. In fact, I'd love to. So I will, sort of my next point was actually going to be about how program repair as a problem is really about kind of fundamentally what does it mean for a program to be correct in practice. And I don't think we know, right? And I don't know how, but I think the fact that we're continuing to ask these questions and refine what repair quality means and how we measure it, and is really driven by this desire to fix programs automatically, is sort of a fundamental reason I think it's an interesting problem. But if we want to think about the lessons about how we got from 60,000 lines of code to 6 million, I think if you want my sort of offhand prediction, I think the really important one was actually scalability. I think that that's really the one that, you know, it needs to run reliably and quickly. I think we have made a lot of progress in understanding fundamentally what repair quality is. I think the patches produced by all techniques in program repair have gotten better over the years, but I actually think that this is less important than scalability when it comes to industrial uptake. The other thing, at least certainly in the Facebook work that's happened, is that this idea of expressive power is less important in practice than it is in the research setting. Instead of trying to fix all bugs, you know, constraining it just to, for example, null pointer exceptions, where you know you can fix those very quickly and well in practice, has industrial uptake, that they'd rather a narrow but known effective approach than the sort of broader use case. But that means that that's left, you know, expressive power open for us as researchers as an open set of problems, which I think is very cool. So in terms of researchers, you know, at the summer school, so I think that there's a lot of really cool work lying between expressive power and repair quality. Scalability is effectively solved, although I think there's still a lot of work to be done in fault localization, especially. But, you know, for expressive power, there's so much work to be done. A lot of the patches produced by existing techniques are quite short, and there's nothing wrong with that. You know, a lot of important bugs are fixed by small changes, but it'd be really cool if we could make more complicated or compositional or multi-part patches. There's so much opportunity for more existing static analyses or dynamic analyses to inform that kind of work. And it's a wide open space. So if you want to solve that, you've got a dissertation right there. But that requires us to understand more about partial correctness, about repair quality, about how can we tell when something's half fixed and then compose them, or compositional repair quality. I mean, there's a lot going on there in terms of how you can measure that. There is, you know, I alluded to this in sort of an off the screen question. There is increasingly actually a huge amount of work in machine learning. Machine learning researchers are beginning to publish on program repair. And so I have to start paying attention to like machine learning venues way more than I've had to in the past, because they're making a lot of really cool progress here in terms of making programs better. And so there's a lot of work to be done in learning new ways to use machine learning to inform patch construction, which again challenges to think about, you know, what should we be learning over, right? Are human informed repairs better? Or do they just look more like what we expect? And I think there's a lot of work in tooling and sort of developer processes to integrate into existing QA processes. And that's cool because it gives us sort of additional non-test signals available from the development process to inform better patches. So not just tests, but you know, documentation. Could we use NLP over documentation to figure out what code is supposed to do and have another way to check that it's correct? Can we automatically document our patches? You know, I mean, there's a lot of other work here to be done to think about how these kinds of tools should integrate into the complex socio-technical system that is software engineering right now. And that's one of the reasons I think this is such interesting things to do, because historically code generation, like compilation or synthesis, hasn't been expected to produce code that humans interact with. Whereas here we're kind of increasingly envisioning tools or bots that humans will interact with their code and need to understand and maintain it. And that's a very different kind of paradigm for these kinds of tools and how they interact with people. So if I can wrap up, I said 5 minutes. That is my baby. That is not my cat. My baby is now 18 months old, but that was when she was small and extremely skeptical. So these were just the lessons that I went through for program repair from my career, from program repair overall. I did consider having my little bug pop up one more lesson and say, program repair is cool, but that seems too corny. But hopefully this has given you a flavor of where the work came from, and a little bit of some of the innovations that got it to where it is today. But most importantly, I think why program repair is still an interesting area and why there's still a ton of work to be done in understanding how to fix bugs well, and what it means to fix bugs well. As well as sort of some lessons from my own career, and my observation of the work that I did as a PhD student and how it has evolved over time, and how we can think about how work gets from very like nascent beginning stages to industrial impact. I think that there is some sort of interesting lessons there. I did mean to caveat this talk at the beginning with a caveat about survivorship bias. That's one thing about doctoral symposium talks, that it's like, well, hindsight's 2020, and here are all my lessons, and I think you take all advice with a grain of salt. I think is what I'm trying to say. No career is actually as linear as they sound in doctoral symposium talks. But I do think that there's some interesting lessons to be drawn from this. So that is my summary. I see it's about 5 to 1 my time. If there are any additional questions, I'm happy to take them. You're also welcome to email me or DM me on Twitter or whatever. I'm always happy to talk.
Okay, thank you so much. That was really, obviously one lesson, maybe even lesson 0, is to do what you love. And you clearly have a lot of enthusiasm for program repair. Make it sound very appealing.
I have a lot of enthusiasm for software quality. Like I said, it's not the only thing my work that I do anymore because I'm old and have a bunch of grad students. But I think software quality is a really interesting question. Is this software is this medium we invented that we don't understand, and that we build these really complicated systems that like barely work, and yet they do, and I think it's great.
Yes, I think you said in one of some other talk I saw that programmers are involved in a war against all these bugs. So these are war times.
It is.
Okay.
I also think there's an interesting thing here about how software is very robust, right? That despite the fact that it's totally broken, it does work, which, testament to human ingenuity, maybe. Yes. Anyway, thank you so much for having me. I really appreciate it. I apologize for the internet issues at the beginning. iPhone tethering to the rescue.
It was fine. So if anybody still has a last minute question, please put it on Slack. And otherwise, I must tell you, I've never conducted one of these sessions, so I don't know if we clap, but perhaps we better not. We might break.
There's a little clap icon. I do know that. It's in reactions.
Of course, yes.
Okay. I can I can imagine.
Okay.
Yes, thank you everyone for your time, especially on a Saturday, calling in from all over the world. I hope soon to be able to see you all in person.
I think that was well worth anybody's time. Okay, right. So now I must ask all the people from the summer school. Let me just switch on my face. Oh, there we go. I must ask everybody from the summer school, not the doctoral symposium, but the summer school, to please leave this Zoom meeting and move over to the summer school Zoom meeting. And I guess maybe, Italo, you can post the link for that somewhere again, because I don't have the technical skills to post a link. Okay. And Claire is leaving, and she says goodbye. And
hey,
I
Jacob.
think... Yes.
Sorry to interrupt. Yes, the next summer school session will be in a bit. So we will post the link on Slack in the summer school channel, and then people can join from there.
Excellent. And I think it may take a few minutes. So maybe we have about 20